The U.S. Post Office will accept a box for shipment only if the sum of height and girth or distance around a bottom is at most 108 inches. Find the dimensions of the largest acceptable box with square top and bottom. So first I'm going to actually draw a diagram of the box, and it will look like this. So it's just a square box, and it'll have a height of h and then bottom dimensions of x and x, because it does say that it's a square box. So the length and width would actually be the same. And so we can just label them as x then. So we know that our first equation is actually in the problem, because it says the sum and then equal to 108 inches. And so we can therefore make an equation that is 108 equals the sum of height and girth or distance around a bottom. So height, which is h, and girth, which would be 4x, because it says that girth is equal to the distance around the bottom, and we know that the bottom dimensions are x and x, and so since it has 4 sides, we would just multiply that by 4, so 4x. And then the function that we will actually optimize is volume, which is equal to x squared times height, and we're choosing this function because we're able to single out the x squared and only use one variable by solving for h using the top equation. And so we would then do that by setting h equal to 108 minus 4x. And so now that we have that equation, we would then just plug that in for h down here. So volume equals x squared times 108 minus 4x. So before we can actually do anything, we need to distribute this. So 108 x squared minus 4x cubed. And so that's our volume equation. And so just to recap, all we did was find the function that it gives us in the equation. So 108 equals 4x plus h, so the height and girth. And then we're using the volume equation to optimize and find the dimensions that are the largest that are acceptable for the U.S. Post Office. And so by doing this, we are helping solve for x. And so the next step would be to find the derivative in order to find the critical number, or what x is equal to. So we would do 2 times 108 and then subtract 1 from 2, so it would just be x, because that's the derivative of 108x squared. You take the exponent and you multiply it by the coefficient, and then subtract 1 from the exponent. And you do the same down here, so 3 times 4, which is 12, and then 3 minus 1, which is 2. And so then we set that equal to 0 to find the critical number, and we would add 12x squared on both sides, and then divide by 12x, which gives us x equals 18. And so we have this number that x can equal, but we now need to know if it's actually going to be a max or min. So we solve for, let me rewrite the first derivative. We solve for the second derivative and then plug our critical number, which is 18, into it, and figure out if it's a max or min using the second derivative test. And so we need to find the second derivative. So we would multiply the exponent by the first number, which is 216, and then subtract 1 from the exponent, which leaves us with just 1. And then we would do the same for 12x squared, so 24x, because 2 minus 1 equals 1. And so then we're actually going to plug in our value, 18, to see if plugging it in gives us a negative or positive number. And so we do this and we find that 216 minus 432 is equal to negative 216, which we know is less than 0, which means that the value 18 is a maximum, and is a maximum for the original function v equals x squared times 108 minus 4x squared. And we learned that 18 is the value we need in order to find the maximum acceptable dimensions for the box, because it's largest, which means maximum. And so from that step, we now plug our x value into the height to determine what the height is. So 108 minus 4 times 18. Sorry, I'm sick. And this means that height equals 108 minus 72, which leaves us with height equals 36. So what we've learned so far is that height equals 36 and our width and our length are both equal to 18 because it's a square bottom, so the width and the length are equal. And the total girth, so if we're labeling that G, is just 4 times x, or width times length, which equals 4 times 18, which is 72, which we've already figured out. And so using this problem, we have figured out that the largest dimensions of the acceptable box for the U.S. Post Office would have a girth of 72 with a width and length of 18 each, and then a height of 36. And so we used the first derivative to find the critical number, and then we used the second derivative to find out if it was a max or min, which is what we did down here. And then we plugged it into our original equation to figure out what the dimensions were. And so interpreting the actual meaning of our answer, we learn that the maximum height and width and length that will give us a sum of height plus girth equal to 108 is 36 and 18.